So this compare and swap is the building block, the fundamental building block that other synchronization operations are going to be built on. It's too low level for most purposes. It works great for just modifying a single number by itself, because compare and swap just can change number-sized things at the processor level. But it's too low level for most things we want to do, like if we want to update multiple numbers at once consistently, or if we need to update a data structure that involves many pointers. Right? Compare and swap can be useful occasionally, but usually it's the building block inside that is used to build other synchronization operations. As we look at locks, then the first concept we encounter is the notion of a critical region. So our problems with incrementing counter is that no two threads should have been trying to operate on the counter variable at the same time. So this pink area we would call the critical region in this particular bit of code. Only one thread should be in this bit of code at a time. And using locks, the way we enforce that critical region is take a lock on the way in, then do whatever's in that region, and then release the lock on the way out. So these lock and unlock operators, which are not the actual function names, but just abstract names for now. You think of lock as you go into a room and you lock the door, so no one else can get into the room at the same time. The room is the critical region, and then when you're done with the critical region, you unlock the door, and then someone else can come in and lock it after that. And this is a generalization of compare and swap in that we can have any amount of code in between the lock and unlock. The critical region doesn't have to be just a variable update. In this case, we're looking up something in a table, which might be many instructions itself, and then based on some other calculation deciding to update the table, which can be many more instructions, maybe even some allocation and so on. But if we put all of that between lock and unlock, then it's a critical region and only one thread is going to be in this region at a time. Sometimes it's not that particular bit of code can't be executed at the same time, but it can't be executed on a given object. So suppose, for example, we have many tables instead of just one table. It's okay for different threads to be concurrently updating tables as long as they're different tables. So we might have some locks where each lock is specific to a particular table, and that code might look like that. So locks can be more fine-grained than just static regions of code as critical regions. They can be associated to objects in this way. And then a final use of locks is that they can act as a signaling mechanism. So here I have something that looks similar to our Echo server. We're creating a thread, and then that thread's going to go. But the thread is supposed to use a value here that's initialized by the main thread after the thread is created. And absent these lock and unlock calls, there's nothing that says this value would get updated before the Go thread starts using it. But with this lock here, it's acting as a gate to keep the Go thread from going, because the main thread takes the lock before it creates a thread, and it doesn't release it until after value has been set. And so the Go thread will have to wait here until value is ready to be used. In other words, it's a kind of signal to say from the main thread to the created thread, it's okay to proceed at this point. If your locks are flexible enough that the locking and unlocking thread don't have to be the same, then you can use the locks to signal the other direction as well. So here we've got lock and then lock. This only makes sense because after we create the thread, then the new thread performs an unlock after its initialized value. So the signaling is going the other direction. In this case, the created thread is supposed to initialize the value, and the original thread is waiting. This will work out because this creating thread has to wait for the lock to become available again, and that will become available in the child. This pattern only works if the thread that takes a lock is allowed to be different than the thread that releases, that balances that lock call.